Well, good morning. Hi, everybody. Thanks you made it to my session. Although I've got fierce competition there who is not, who even tries to hijack the audio. There are 4 sessions running right now, and the speakers are 5 CTPs. So it's pretty high-class content everywhere, I suppose. My name, as you probably be able to read, is Helge Klein. I'm at Citrix CTP. I'm a Microsoft Most Valuable Professional. In my kind of spare time, I write tools, some of which are pretty popular. One of those is XenApp. It's a free permission management tool. It's been downloaded roughly 500,000 times already. Another tool is delprof2. It's a profile deletion command line tool. It's also free. It's a successor to the delprof utility, which Microsoft provided, which is incompatible with Vista and newer versions of Microsoft Windows. Apart from that, I try to earn my money as an independent consultant and developer. Before I became independent, roughly a year ago, I worked for Sepago, which is a German Citrix Platinum partner. Sepago is kind of well known for its profile management tool, which used to be called Sepago Profile, which got bought by Citrix and is now called Citrix Profile Management. And I was the original architect of that product. Now, in the next roughly 1 hour, we'll be talking about XenApp sizing, of course. I got asked yesterday whether I was going to be teaching an Excel masterclass. Definitely not. This is not about number wrangling. It's about, I've developed a methodology rather, to look at an existing farm, determine the load and the capacity of that existing farm, and from those numbers and from that understanding you get during that process, to be able to set, to develop how the new farm should be sized. So it's, we look at A, and from A we go to determine B. So I hope that's at least somewhat scientific and a little more precise than what people typically do. When I initially researched the subject, I was astonished that there's nearly no information about sizing on the internet. People seem to just do it, well, I buy one server that works well, let's buy 50 of them, and if it's not enough, let's buy another 20. Apparently it works something like that most of the time. I try to be a little more concise with it. And there will be a lot of theory. I hope you bear with me, and if it gets too boring, just let me know, or if there's something too fast or too slow, just interrupt me. Now, the way I'll be doing this, I already hinted at it. Well, we'll be determining the capacity of an existing farm. We'll try to measure the load and identify bottlenecks. Is the farm limited by CPU, by disk, by memory, by whatever? And then we'll be able to extrapolate from that. Do we need, for example, more CPU capacity, or even less, or more network capacity, or whatever? To give you an example, what we're trying to achieve is, this is the result of this talk. I'm concentrating on these 4, what's that pointer? I'm concentrating on these 4 main components of each XenApp server, which is RAM, CPU, IOPS, hard disk performance, and network. For each of those components, I'm going to calculate the total capacity of the existing farm. So what do we have sitting in the data center? Then I'm going to break that down to get values per user. total capacity of a couple of gigabytes or whatever, that's nice, but it doesn't tell me anything if I don't divide it by the number of users. Only then do I get meaningful numbers. Then, in the next step, thank you, Rick. In the next step, I'm determining the factor. Do I need more of it or less? As you see in this example, we determined a factor of 2 for RAM. So apparently, RAM is there's not that much RAM available at the old farm. Of course, in the new farm, after that, we'll have more RAM per user. And after that, we'll get a total amount of RAM for the entire farm. And with those numbers, we can very accurately size our servers. But that is the end result we're going to work towards. Now, those are very nice numbers to have, but they are not so easy to get. What we'll be doing to get those numbers is first there's several data sources we can use. We can collect data, we can observe, which is also always a very powerful tool scientists have been using for thousands of years. Then we'll take measurements and also a couple of simple calculations. Let's start with some data collection. Where do you get data from Windows servers? What do? You use perfmon. Perfmon is going to be it's coming later in a minute. There's another repository of information except for the performance counters that is pretty vast, that contains nearly anything you might want to know about any Windows system. That's WMI. Unfortunately, WMI is as vast as it is, as poorly documented it is too. So it's pretty hard to find out if you want to get some specific information. Is it in there? Probably yes. Where is it? Okay, don't know. And how to get it out. One way to deal with WMI is a nice little command line tool called WMIC, WMIC. You'll see it in this command line right there. And you can use WMIC to query the WMI database of a specific system. In this case, the system is identified by the parameter /node. And this is a simplified syntax which WMIC allows you to use. We want a certain information about the CPU of each system, like the name, the clock speed, description, and some other stuff. We'll query that for every server in our existing farm. For that, we need, of course, a list of all the servers in the farm. In this example, the list is called allfarmservers.txt. And with this nice little batch command, the for loop, which is pretty powerful, comes in handy very often. We run that command on all servers in the farm and write the output to a file called cpus.txt. Now, you might wonder where to get that allfarmservers.txt list. It's one easy way to get it is with the command qfarm. Now, the resulting list, this file cpus.txt, looks something like this. There's a lot of data in there, but it's not, well, we need to work with it it's pretty hard to interpret it like this manually. But what you can see, there's one line per core. So the first column is the system name. So we have for this server 001, we have 4 entries, which means it has 4 cores. So probably one CPU with 4 cores. Now, we could try to gather information about the other components of a system, like RAM, network interface cards, hard disks, and other stuff. Similarly, so we could create more WMIC queries to query WMI for all the other stuff in a specific system, but then it would become, we would get only more data, but not really more information. That is irritating from time to time. Now, we'll try to make things a little bit simpler by postulating that probably the customer has only a specific number of server types in his data center. We only need to know how many of each model do we have. So we put together spec sheets for the models that are in place. For example, this customer, one of the models of this customer, all these numbers here are actual, are from a real life example, by the way. So this customer has HP DL360 generation 4 models in his data center. So put together the relevant system components in a G4 system. And by putting together this list, the list we generated earlier, this one, and checking for how many CPUs of this type we have, we get, as a result, how many G4s are in that data center, and also other types of servers. As a result, we get something like this. So you see various generations of HP DL360 servers in the data center with the numbers for each. Some customers may have asset data that tell you this exactly, but so you can omit this step of manually gathering the data. But I've come to learn that asset management systems, if they are in place, they typically contain stale data, and it is not very advisable to rely on that if you need to know what's really down there. Now, we know roughly we know pretty exactly what is in the data center right now. Now, what are those servers doing? If I want to know what a system does, I'll use a pretty powerful tool that's very much underrated in my opinion. That's Task Manager. It tells you many things that are very interesting and relevant about a system. So you can, by clicking around a little bit, you can see how many users are logged onto that system. Do they have high user counts or low user counts? 50 users per box or only 10? What are the components doing, like CPU, RAM, network? Do we have many processes running? Only a couple of processes? Do we have individual processes with a very high amount of very high memory demand? For example, Java processes, .NET processes are good candidates for that. .NET is in no way better than Java when it comes to memory consumption, by the way. Java, only the reputation of Java is a little worse, I would think. So by looking at Task Manager, we get a first impression of what might be going on with this system. There's only one thing Task Manager does not tell you of all the relevant counters and components, and that is disk activity. That is unfortunate because disk activity is obviously very important to a system's load. And Microsoft has seen this too and added disk activity counters to Task Manager in Windows 8. But until everybody is on Windows 8, we need to find additional methods to determine disk load. For this, we have to rely on, go to the performance counters. And there are two performance counters that are pretty interesting when it comes to determining disk activity. One is percent disk time, which is roughly equivalent to the flickering of a disk LED. So if percent disk time is at 100, the LED would be constantly, it wouldn't be flashing, it would be constantly on. If percent disk time is at 50, it would be flickering regularly. And another thing is average disk queue length. many components in a system, in a Windows system, have a queue. So if different processes try to access the disk nearly simultaneously, obviously the disk cannot process all these requests at the same time. So Windows needs to queue these different I/O operations and send them to the disk one after one. Obviously, a long queue is not good because it stalls, and I/O operations makes the system very much slower. The perfect average disk queue length is therefore 0. We don't, in a server, we don't have that. If we do, the server is probably, the disk subsystem of that server is probably not, it's too big. It's not sized properly. There should, if there is disk activity and a server should do work, that's why we bought it for, then the disk queue length is going to be above 0. Now, how big can it be, or should it be? There's a rough number. Microsoft recommends it shouldn't be higher than 2 per physical disk, per spindle. If it is at 2 or even higher, that spindle is considered fully loaded. Now, if you have a RAID, you need to take care which disks are actually working. So, for example, in RAID 0, we have with two disks. We have striping. We have both disks are working. So the maximum would be at around 4. If we have a RAID 1 with 2 disks, only one disk is actually working. The other one is a mirror of it. So the maximum is at 2. If we have a RAID 5 with 3 disks, how many are working? 2. So the maximum should be at 4. But those are rough guidelines only. Okay, after looking at Task Manager on several systems and looking at these disk performance counters I just discussed, in this specific case, my hypothesis was that the farm is memory limited. That was my impression because I saw many processes, many Java processes consuming huge amounts of memory. And the customer confirmed when I talked with him about it, yes, on average we only have about 7 to 10, something in the area of 10 users per box, which is not very much. And they couldn't get many more users on the box because they have these Java applications with a huge memory demand. So this conclusion is preliminary for one, and is of course, it is different in every environment. So I'll be talking through this one specific example, and your numbers will of course be different. Now, this is an hypothesis only. I wanted to confirm it. So after the first observation step, I took measurements. The tool for that is, of course, perfmon and its performance counters. Let's take a look at the performance counters that are interesting to get an idea what the server is actually doing, how is it loaded. First, some counters that give me an idea about the general system information, active sessions, inactive sessions, total sessions, that's always nice to have, and the list of the processes just in case. Now, when I want to take a deeper look at disk activity, I include the 2 counters I discussed before, average disk queue length and % disk time. But there's some additional counters that are very interesting. In my opinion, those are disk reads per second and disk writes per second, which is equivalent to read IOPS and write IOPS. I'm sure you know the term IOPS, which has gained in popularity quite a lot with VDI. And then another thing that's interesting is the latency. How long does it take for a specific disk command to actually complete? And the counter that tells me that is average disk seconds per transfer. How many seconds does it take for a specific transfer to go through? Now, as you can see here, we've got 5 counters for hard disk activity, which is an indicator for the fact that it is pretty hard to determine what the hard disk is doing and how much it is loaded. For the other 3 relevant components of a system, we only need 1 counter each. That's percent processor time. That's good enough for us. With that we know pretty well what the CPUs are doing. Then we have memory available bytes. Sorry. That one is a little bit tricky because I don't really want to know how much memory is available. I want to know how much memory is being consumed. But there's no performance counter telling me that. So this forces us to first determine how much RAM a system actually has, and then subtract from that these available bytes, and we get the number of megabytes that are consumed. But the last one, network interface, that's very simple. With regards to the network card, in a XenApp server, I'm only interested how many bytes go through. Network usage is, in many cases, relatively simple in a XenApp server, so that would be sufficient. Now, I want to gather all this information from a substantial number of servers in my farm. So how do I go about that? Do I open perfmon on every single server and click through the list, the counters, add them, and have it start a data collection for example, 24 hours? I could do that, but if I want to do it for all servers in my farm, or even only for 20 servers, my fingers would go numb from clicking, and it's not very funny. That's not the thing, not the way you want to spend your time. So again, we use a tool, a nice tool for interfacing with performance counters is Logman. It's been there at least since Windows Server 2003. And as you can see, so what are we doing here? We have Logman create a performance log, create a counter, okay, to be more precise. We give that a name, tsperf. I could have chosen any other name, it doesn't really matter. Now, I tell Logman to please log in the in CSV format, comma-separated values. I could have chosen a binary file too. Doesn't. Both are. Those are the possibilities I have here. I specify the file where the data should be written to. C perf logs counters.txt. Oh, sorry. Mistake on my part. Read the counters to process from that text file, counters.txt, and write the output to one server13.csv file. Now, sample interval at every 60 seconds. So take one snapshot every 60 seconds and write the current data to the output file, and run for 24 hours. Now, that's pretty nice. It saves me from clicking in perfmon on this one specific server, server 13. But I can improve this, of course, if I want to process many servers. I can run it remotely with the additional parameter -s. So I can run the command, type the command on my workstation, and run it on server 13 anyway. And I can run it very easily on many servers in my farm with the very, very helpful for loop. I'm a big fan of that one. For that, again, I need a list of these servers in my farm, or at least the servers I want to process. Those might not want to process all, but only a subset of all servers. This line should contain one server name per, this file should contain one server name per line. And yeah, that's about it. That starts the performance data collection on as many servers as I like for 24 hours. After that, now, when those 24 hours are up, the interesting part starts. Then we get to analyzing the data. What have we got? What does the data we gather tell us? Now let's start. Sorry, let's start with the CPU. I open Perfmon and direct it to that CSV file generated for one specific server, and load two counters. So in this one and the following graphs, we always have two different lines showing. One is the red is always the user count. The yellow is something else, in this case the CPU, and we'll be looking at the other system components too, of course. And the duration, the time span of this is roughly 1 workday. So you see, in the beginning people are logging on, so the red graph goes from 4 active sessions to 12 and then settles at 11. As I told you before, that is not very much. Those machines don't have many users on them. And while the users are logging on, we see the yellow line. I hope you can you see that? Or somewhat. The yellow graph goes a little up. So there's a little CPU activity during logon that's creating the user session, loading the roaming profile and stuff like that. And then after that's done, the CPU is basically idling away. The graph is scaled in such a way that at the top here there would be 100% CPU utilization. So, sorry, CPU, that's 200 up there, so 100% CPU utilization would be right in the middle. But still, the CPU is not really doing anything. And that's not good. A CPU that's idling means I've spent way too much money on CPUs. The CPUs are there for calculating, for computing. That's why it's called a computer. So, the CPU load of something in the range of 50 to 60 or even 70%, I would deem acceptable or even good to have in a XenApp server. So it looks like we have a lot of overcapacity with regards to CPU, at least on this one single server. So let's look at a different server. We look at the measurements on the same graph, only a different server. And you see, it's very similar here. The user count is increasing and then relatively constant, and a little bit of CPU load during the morning logon phase, and after that, next to nothing. So this, it looks like the data from the second system confirms what we saw on the first system, but we don't know yet. Are these exceptions, or are all servers like that? So how do we find that out easily? So for that, I generated a graph where I overlaid the CPU usage of all these servers. This is going to get crowded, but I can see easily in which range the CPU usage is for all those servers. Now, it's pretty clear that all these servers, well, although I cannot really see how high the CPU usage of an individual system is, but all are in the same range, near zero. So we now know that CPU-wise, the farm is not loaded at all. We have overcapacity. Now, we use the same procedure for the other system components. Next, hard disk usage. We've here in this graph, again, red is the user count, the session count to be more exact, and blue is the average disk queue length. And the scaling is such that at the top we have the number 200. That means an average disk queue length of 2. And you remember, for a single spindle, that would be roughly full load. In this case, the system has two spindles, 2 physical disks, configured as a RAID 1. So only one disk is really active. The other one is just backing it up, more or less. So the top of the graph would be full load in this case. And well, what do we see? During the logon phase, we get a lot of disk activity. Why? Profile loading, which I think this is very typical for most XenApp servers, which are, of course, stateless. When a user logs off, everything gets deleted, his profile, temporary data, stuff like that. And when a user logs on, everything needs to be brought in again, which causes quite some hard disk activity, as you can see. After that, we have very low numbers here in the same range as the CPU graph we had before. But I wouldn't say that this is, should be interpreted the same way. A CPU that does nothing, in my opinion, is that's not good. It should do something. But a hard disk, a disk queue length of, let's say, 0.1 or something, doesn't mean the disk is doing nothing. It means the disk is pretty active and that there are always, all the time, requests waiting. Not many, but there are requests waiting. So if that graph is here at the top, that means the disk is so loaded that requests need to wait pretty long, which is not very good. In this case, it'll slow user logons considerably. And yeah, ideally, you'd have a disk queue length of 0. But again, if a server is working, that'll be hard to achieve. So all in all, I would say this server has a moderate disk load. It shouldn't be much higher, but there's little room for growth, so to say. Let's confirm this, try to confirm this by looking at the data from a different server. It looks roughly similar. The lines are not exactly identical, of course. There's a different server, different users doing different things. But still, during the logon phase, we have a peak. And after that, the disk is, well, it's doing something. So let's look at all these servers. The overlay. Is this typical, what we see here? And there's a little, again, it gets pretty crowded, but it looks somewhere in the region of what we saw before. During the day, the disks do work. They're not fully loaded, but they are doing, they're spinning, they're rotating, they're accessing lots of files. And during the logon phase, there's more. So let's say we have typical or moderate disk load. Now, next look at RAM. As I mentioned before, there's no performance counter telling us how much RAM is actually used, but only a counter telling us how much RAM is free. This is a little bit unfortunate because of that the graph looks funny, but of course in the beginning, in the morning, we've got lots of RAM available. The green line is very high on top, and it gets less and less. So in the afternoon, we have roughly 400 megabytes available on this specific system. So what do you say? Is the RAM fully used? Doesn't look like it, does it? There's roughly 400 megabytes left that could be used by something. But this is a little bit misleading. Those 400 megabytes are used by the file system cache. you know, of course, that Windows tries to use as much memory as possible for caching hard disk operations. And that cache is extremely important for the performance of the system. So basically, there cannot be too much RAM in the hard disk cache. And what we have here is a pretty low number, in my opinion. So I would say that the RAM is pretty much used up. The system could assign these 400 megabytes to applications. That would be possible, of course, but then any time a file is requested, that is, the system needs to go to the disk and fetch it, and that takes long. And the user will notice that by delays. Starting applications, clicking around applications, bringing up dialogues that have not been in memory before, stuff like that. So let's look at the second server again, and we have a similar graph. The numbers are not exactly identical, of course, but it starts very high and then goes continuously down. In this case, the number is probably 500 megabytes of free memory at the end of the day. Now let's again overlay overlay the memory usage of many servers. In this graph, the time span is a little bit longer. So you'll see the morning, you'll see the day, and you also see the afternoon or the evening when people are logging off. So memory is being freed again. Yeah, so we can roughly confirm that the free memory is in the area of 500 megabytes. As I said, that's not that much because file system cache should get as much memory as possible, and secondly, this is not the heaviest day of the year. There are days when many more users are logging onto that system. I think November is the month with the lowest rate of people off sick and on holiday. So yeah, I conclude that more memory certainly would help this server. Last thing to look at is the network load. Here the graph is scaled in such a way that the number 200 on top means a throughput of 2 megabytes per second. And if you look at this graph, the average transfer rate is somewhere in the area of 200 kilobytes per second. Now this is a 1 gigabit card which can transfer roughly 100 megabytes per second, and of that 100 megabytes, I only use 200 kilobytes, which is, well, next to nothing, so this card is idling away. A lot of overcapacity in this server. Second server looks very similar. If we overlay all those, the data from all those cards, well, we get the same picture. Network cards are basically redundant. We could replace this 1 gigabit card with a 10 megabit card, and people wouldn't notice, I assume. Now, after looking at all these graphs, I would say that the hypothesis that this farm is limited by available memory could be verified. And, well, we have low CPU load, negligible network load on the network card, and, well, somewhat in the area of moderate hard disk load. Now, with this information, let's get back to the table I showed you in the beginning. We can now start to calculate farm capacity. So let's see how we can do that. To know what a farm is capable of, we'll start by the CPU. To know what the farm is capable of, how much horsepower it has, we need some way of adding up the performance of all those CPUs in the data center. Now, it's pretty hard to compare different types of CPUs. As you know, the amount of the megahertz count, it doesn't go up all the time. The CPUs are in the area of 2 to 3 gigahertz, have been in the area of 2 to 3 gigahertz for a long time. So how do I compare a Xeon CPU from 2006 to a younger model from 2009? I need to be able to say, okay, this CPU has a relative performance of 5, let's say, and the other one of 10, so it's probably roughly twice as fast. And if I add the performance, I get a value of 15. But which numbers to use for that? I could have run benchmarks on these servers, comparing the CPU benchmarks that give me some value for the CPU performance. But benchmarks have several downsides. For one, they take time to run. Secondly, I would need a free server without users, and one server of each type for a certain amount of time to run my benchmark. And thirdly, well, benchmarks often cost money. And the fourth thing, benchmarks are pretty inaccurate. A benchmark, there's no objective benchmark. A benchmark runs a series of computations and spits out a number. If you run different computations, you get different numbers. So, in my opinion, benchmarks suck. They're not very helpful in many situations. And if you use benchmarks, be very clear about what that benchmark is actually doing. So I didn't use benchmarks. Instead, I used something completely different, and well, that is Murphy's Law. No, Murphy's Law is a good thing to use, but no, I used Moore's Law. Moore's Law postulates that CPU performance doubles every 18 to 24 months. Moore's Law was formulated by Gordon Moore in the 70s, which is was very long ago, and it's still it's still being proven to be valid every single year. How is that possible? The answer is pretty simple. It is accurate because hard disk CPU manufacturers use Moore's Law to time their product releases and to time how they build new factories and stuff. So it's a self-fulfilling prophecy. And because Moore's Law is pretty accurate, we can compare the performance of different CPUs relatively easily. We have a graph that tells us, Moore's Law is basically a graph that tells us if a CPU is from this year, its performance is here, and if a CPU is from a different year, if it is younger, it's there, it's higher. And I can calculate the difference in performance between those two CPUs extremely easily with a simple formula, e to the power of 0.033 t, and t is the difference in time between the releases of two different CPUs. So I just need to fill in t, and I get a value. So to put this to practical use, I set the performance, I define the oldest CPU in my farm has a relative performance of 1. And then I get something like this. You see, the oldest CPU here was this Xeon 7100. It has 2 cores. It was first sold or released in 2006. And I give this a performance rating of 1. Next, the next best CPU, it's a little faster, you can see. It was released a couple of months later. The difference in months is something 7 or something. I fill that number 7 in, put that in the formula, and I get a value of 1.26. Now, this two decimal places, the 2 places after the comma, that should be not a comma, that should be a point. Sorry, comma is used in German in that place. But anyway, the difference is roughly 25%. It's not as accurate, of course, this methodology as this indicates, but it gives us a pretty good understanding of the relative performance of these various CPUs. So we can say with some accuracy that the newest CPU is roughly 4 times as fast as the oldest one. And if you break that down per core, the newest CPU has twice the amount of cores, as you can see. The relative performance per core is roughly factor 2. Now, if we create a table with each CPU, with each type of CPU, we list the number of those we have. We multiply it with the number of cores per CPU, so we get the number of cores here. And now we multiply this with this number with the relative performance of each core. We get this number for CPUs and for cores. We add it up, and these are normalized numbers. They can be compared and they can be added. So I add up these, and I've got 1,250 normalized cores in my farm. Meaning, if my farm, all the servers in my farm only had this CPU, I would have 1,250 of it. Okay. So if we break that down per user, so this should read normalized cores. I've got 0.63 really cores per user, which is quite a lot, I would say, depending on the workload, of course. But this is an office workload, so people typically don't use that much, don't need that much CPU performance. So this number is relatively high. But I find it pretty interesting to get numbers per user suddenly. This is something we can work with. 1,250 CPUs or cores or whatever, normalized or not, that doesn't tell us very much. But if we know so and so many CPUs per user, that's something completely different. Next, hard drive performance. This, as I said before, it's pretty hard to measure accurately. Since I needed one value telling me what the performance, the available performance was, I chose IOPS, input-output operations per second. IOPS are relevant if you have high concurrency in hard disk access. And in a XenApp environment, we do have that. We have many users on the system, and each user typically has several processes running. So we have a very high number of processes that each do something. Many do access the hard disk, and because of that, we have high concurrency in hard disk access. If we had a different scenario, if we had only one application, and that application would be writing large amounts of data, and reading or writing, it doesn't matter, then IOPS wouldn't matter at all. Then the throughput of the hard disk would matter. The rate of how many megabytes or how many 100 megabytes can I read per second. But in that high concurrency situation we have in XenApp, throughput is nearly irrelevant. IOPS are much more important. Now, measuring IOPS, we saw before which performance counters we can use to measure IOPS. Again, disk reads per second and disk writes per second. Now, we'll get some numbers here, and when you compare these numbers to what hard disk or SSD vendors promise you, that's always something, well, it's something tricky, because depending on the way I generate IOPS, those numbers can be vary very extremely. There's one very powerful tool that's published, I think usually originally published by Intel. It's IO Meter. It's open source. The latest version is from 2006, by the way, but it still works pretty well. And you can use IO Meter to generate IO load. And there are many parameters you can vary to generate different types of load. Do you want to have read access, write access, random access over different areas of the disk, or continuous sequential access? What is the block size? Do you want to read or write 4K blocks, 512 byte blocks, 10 megabyte blocks? And depending how you choose these parameters, the IOPS rate you get will be extremely different. And when a hard disk or nowadays SSD vendor tells you, oh, my device, it makes, I don't know, 100,000 IOPS, that's pretty nice, but that will be only in a very specific set of perfect conditions, and you're not going to get those perfect conditions in your production environment. So don't believe vendors, they lie. Always measure, if you can, with your real workload, and if you can't create real workloads, then try to simulate it as accurately as possible. But that was a little diversion. In this case, I have a real workload, and these are many servers again, and on those many servers I collected the read and write IOPS. Blue is write, and red is read. As with VDI, once the system has booted up, the read IOPS are much lower typically than the write IOPS. During the boot phase, of course, this Windows reads many files and it needs to load DLLs and stuff and whatever. But once all those DLLs have been read once, they are in the file system cache. And the next time any application is started, the usual list of 20 or 30 heavily used system DLLs needs to be loaded, but they'll be loaded from the file system cache if they are not in memory already. So that's why the reason why we don't have many read IOPS typically, as was the case here. And additionally, we'll be ignoring read IOPS completely in the calculation, because we'll be moving from a physical, non-provisioned, physically installed Server 2003 box to a provisioned box with Citrix PVS. So we are mainly concerned with write IOPS. The average is somewhere in the area of 15 IOPS, with peaks at roughly 30. So for the calculation, I'll be using a value of 30. Always use these spikes when you're calculating with IOPS, because if you don't use the spikes, if you use the average, that means every spike will have the user waiting. If the hard disk each hard disk is roughly 1 million times slower than RAM. So if a hard disk needs to be accessed, and if that takes time, the application will be waiting and the user will notice it. Okay, given this, we have a total capacity of 7,300 IOPS in the farm. If you know the numbers for typical SSD, modern SSDs have write IOPS, even consumer SSDs have write IOPS in the ranges of 10,000 plus. So isn't it interesting that one modern SSD could deliver all the hard disk performance this farm needs? And the farm has roughly 250 servers. Broken down per user, we've got 3.7 IOPS per user, which is, well, relatively low, I would say. Next, RAM. Different than CPU and hard disk load, RAM load or capacity is extremely easy to calculate. I just have to add up the numbers. There's one thing that makes things a little bit more complicated. If you think back to the good old days of 32-bit Windows, you will remember that you cannot use the 4 gigabyte built into a typical server entirely, but only a subset of that, typically something in the area of 3.5 gigabytes. That is because device drivers need memory to access memory addresses, virtual memory addresses, to access the graphics card and other components built into the system. So as you can see here, I measured how much RAM we actually can use in these models. See, it's roughly in the area 3.5 megabytes, 3.449. With the G5, HP, well, I would say fucked it up, but I'm polite, so I don't. They stole 250 megabytes from you, and they gave it back in the next generation. So I would bet that not many people noticed that, but that would, it's a little diverse thing here, but if you replaced one G4 model with one G5 terminal server, you'd probably get reduced performance, at least if you're memory limited. Well, multiplied by the number of servers, we get these numbers, and the total amount of RAM that is actually available to the operating system is 832 gigabytes in the farm. Now, we cannot use those 832 gigabytes. Why not? Because we have the OS. We have roughly 240 instances of Windows Server 2003, and Windows Server needs, of course, memory for itself. So I tried to calculate how much memory that would be. We have the kernel with pooled and non-pooled memory. Mainly, we have the session 0, which is mainly all the device, not the device drivers, those are in the kernel, which are mainly all these services. And then we have the file system cache. Never forget the file system cache, please. And then we get a number of roughly 900 megabytes, which the OS just needs to just run. So, putting this all together, of the 830 gigabytes available to the OS, 630 are available for sessions, for applications, for my users. And the difference is pretty high. And this shows how inefficient 32-bit Windows really is, because we have a 25% overhead for the OS. With a 64-bit system and with more memory, that overhead can get down to the low single percentage values. Now, last thing, network. We have in each server a gigabit adapter, which can transfer roughly 100 megabytes per second. All in all, that's a capacity of 24 gigabytes per second that can be transferred in the entire farm, which is pretty much. That boils down to 12 megabytes per second for each user. And if you remember, the number that's actually used per user is roughly, per server, sorry. Per server, we only use roughly 200 kilobytes. So we have an extreme overcapacity here. Now, with all these numbers, let's get back to that Excel table from the very beginning. We're nearly done. You can get, the boring stuff is about to end. Now, we now know the capacity of the existing farm, both in absolute numbers and in the numbers per user. No, remember, I've got 12 megabytes per second. Network capacity per user, 0.6 normalized cores, and so on. Now comes the part where your experience kicks in. How much more or how much less am I going to need? We determined how loaded each component was. So let's go get through this from top to bottom. We saw that the memory is used pretty heavily. So to have enough memory for the next couple of years and to relieve this memory pressure on memory, you say factor 2 would be good, to have twice as memory in the future per user as we have now. Next, we saw the CPU is not very loaded, so it'll probably be okay if we have only a quarter of the CPU performance per user in the future as we have now. Next, we saw the hard disk is moderately loaded, if not a little bit more. So I would say a little bit more hard disk performance, 50% more, shouldn't hurt. And the last thing, network, there's so much overcapacity that 10% of the existing capacity should be enough in the future. Now, with these factors, I have everything in place to calculate the capacity of a new farm. I take this value, 315 megabytes of available memory per user, multiply it with this, and get a new value. If now I know I need 630 megabytes per user, I multiply it with my user count, which may be higher or lower in the new farm. In this case, it was a little higher, and I get the total amount of RAM I need in the farm. Same for hard disk, CPU, and so on. And so on. Now, the only thing that remains is I need to split this up into individual servers. I can, of course, build a few very big servers or many smaller servers. That depends. What you want to do depends on your preference or your customer's preferences. In this case, for the calculation, I used some parameters, like you can see. The old CCU count of the number of users on the farm was 2,000. The farm was to be increased in size to 2,500. The new OS, we're going to use 2008 R2 here, which has a slightly larger footprint, not 900 megabytes for the OS, but roughly 1,300. Then new CPUs, new servers will be bought, which have of course new CPUs, and the relative performance index of the normalized performance is 1.9 for those. And to get to the number of disks we need, we know the IOPS, but we really need the number of disks. For that, I said if you buy 15K server disks, they might be able to deliver 300 IOPS. That might be a little bit higher. That value depends on the kind of IOPS you have. And then we want to have 50% overcapacity for disaster scenarios. So with these parameters, we can size a server. Now the final task is really simple. How big do you want to have a single virtual server? We're obviously going to virtualize the OS. 32 gigabyte is a nice value. It's the maximum value amount of RAM you can address with the standard edition of Windows Server. And it's a handy value. You could have used something bigger, but 32 gigabyte was fine for the customer. With that set, I can deduce everything else. I will get 50 users per server. I need 4 cores. I need 270 IOPS per virtual machine, which is roughly 1 hard disk, 1 spindle, and 0.6 NICs. So there's a pretty handy size, and I'll be finished in a minute. If we say, okay, we'll put 3 of those virtual servers on 1 physical box, we get pretty reasonable numbers. We get roughly 100 gigabytes of RAM in that system, which is easily possible today and easily affordable. We get 12 cores, which is again very much affordable, 2 6-core CPUs. We get 3 active hard disks, 2 NICs, and a total amount of 50 virtual servers and 25 hosts, again with that overcapacity in mind. And we have a very important number, 150 users per host. That is one number most customers are very concerned about, since, as in this case, they didn't want to have too many users per physical box, because if one physical box fails, all those users will have lost their state and need to reconnect and so on. So, I've got an Excel sheet which does the actual calculation for you. If you're interested in getting it, please just contact me via email, Twitter, or give me a business card, whatever you like. I hope this was interesting, and enjoy the rest of the day. Thank you very much. Is there a question? Ah, very good.
So you mentioned using SSDs to address the IOPS issues. Are you seeing a lot of SSDs in production in XenApp servers? Because I hear a lot of talk, but I'm not actually seeing too many people implement them, the people I talk to.
Yes, well, certainly many people are thinking about SSDs and probably talking too, but from what I see and hear, usage is pretty limited right now, because you cannot just, I take it you're using one of the big server vendors, HP, Dell, IBM, whatever. If you do, you cannot simply stick buy an Intel SSD for a couple of $100 and stick it into it, because you would lose warranty. If you're not warranty, you don't have support for that configuration. If you want to have full support by the server vendor, you need to buy the SSDs from the vendor. And that's the problem. The vendors know that, and they have ridiculous prices for the SSDs. I've recently I could get my fingers on a enterprise performance SSD by HP, which is sold list price something in the area of $11,000, which is completely ridiculous. I measured the performance of that disk, and it is not that good. Now, it might be that this SSD can sustain that performance for a longer time than a typical consumer SSD. That might be possible. I didn't make stress tests for hours on time. But still, such a price tag is so ridiculous that unless you have money to waste, you're not going to buy SSDs. You're going to look for some other way to deliver hard drive performance.
And there still seems to be some concern or prejudice about the reliability over time.
Yeah. The question was regarding reliability of SSDs. Of course, I didn't make tests myself regarding reliability, but from what I've been hearing and reading, reliability has been getting a lot better in the past couple of years. An indicator for that is that the guarantee, number of years the vendor guarantees the drive will operate, the guarantee years have been increased. I think Intel right now has server SSDs that could be used in servers where they give 3 or even 5 years guarantee. That's a pretty good indicator for the reliability, at least the vendor thinks his drives have. So I would think these drives are production ready, especially the newer Intel drives, and similar drives, but you have that silly support question if you put them in your servers. There are vendors out. There are vendors out there like Webtel, for example, who take these Intel SSDs, which are relatively inexpensive, and put many of them in one box and write some software for the management of that box and present all that ridiculously fast and also reliable storage via NFS or iSCSI, whatever. Those systems are very interesting. They are not exactly cheap, but much less expensive than, let's say, a typical Xen vendor, EMC or something. Go to an EMC and ask for SSDs, and you won't believe the numbers, the price tags they'll be putting on the systems.